Welcome back. We said that we're going to now look at the atom. We're going to look what's inside this guy and how do they actually combine together. Remember we spoke about sodium and chlorine and various other atoms that come together with charges and stuff. Now we're going to delve inside the atom and look at how does it actually work, right? It's actually very, very logical. There's a pattern that it follows that allows us to combine various of the elements on the periodic table. Okay. First of all, you've all heard of a proton and an electron and a neutron and things like that. Those are the basic particles that make up the atom, right? Well, first of all, what have we got inside? We've got what we call the nucleus inside, okay? So inside of the atom itself, all right, let's just take, for example, a hydrogen, right? Inside of this thing here, we've got the nucleus. Okay? Now the nucleus is, let's say, is the core. Okay? So if we then say, right, now inside there, this is where we keep protons and neutrons. Okay? Protons, P, positive. Okay? Protons are positive. So inside here we've got a proton. Neutrons are neutral, which means they carry no charge. All right? They just added in, they actually add weight. They're the weight carriers, okay? Now around the outside of this, we've got an electron spinning. It's pretty much like a solar system if you think about it. It's kind of like what I'm holding up here. If you look, we've got the nucleus over there on the inside, if you can see where I'm pointing to. We've got the nucleus on the inside, and we've got over here, we've got our electrons right on the outside, right? Now, as you can see, there's more going around the outside, which indicate that we've got different layers of electrons, because we can't just put a whole bunch of electrons all together. Why not? Well, quite simple. The electron has got a negative charge, right? So the electron's negative charge means we can't just push a whole bunch of electrons together because they don't want to be together. Remember, like charges repel, unlike charges attract. So a plus will push away another plus, a minus will push away another minus. But if I put a plus and a minus together, they will attract each other. Okay? They will want to get together, right? So let's just now think about this. We've got this central core. Let's just take it step by step. We've got one proton of positive charge in the middle. We've got one electron floating around the outside. Remember what we said about the periodic table. What was very important about it is each element in the periodic table had no charge, right? There was no charge on the periodic table. That means that they are in effect neutral. So the number of protons must equal the number of electrons, right? That ensures that there's a balance and there's no charge. They even each other out. So every one of the elements on the periodic table has got that configuration of, if I've got 3 protons in the middle, I've got 3 electrons on the outside. All right? So let's just have a look what it looks like, for example, right? Let's say we've got helium, right? Now, if you look on a periodic table, helium is number 2, right? Each of them are arranged, each element is arranged with 1 extra proton or electron as it goes up. Right? So hydrogen has got, let's have a look. Hydrogen has got 1 proton and 1 electron. This is hydrogen. Helium has got 2 and another electron there and another electron there. I have drawn these electrons like this. opposite sides, right? Because these electrons are spinning around the outside. Like an moon orbiting the Earth, if the Earth is the nucleus or the core, the moon would be an electron sitting out over there. Okay? But they are on opposite sides because they are both negative. So in essence, what we've got is we've got that. If we move along now and we go to lithium, which is number 3, lithium has got electron, electron, and an electron. Now they're not arranged like that. We'll get to how they actually pack in a few moments, right? So essentially where we're sitting right now is we're sitting in a situation of each time we add one, we add a proton in here and we add an electron on the outside over there. And the electron that's on the outside is balancing out the protons on the inside. Which brings us to the way we describe, or a way that is descriptor of it. Okay, you'll see in your textbooks they will have A up there. I'm using exactly what you've got. This is the element here, or the symbol, okay, for it, and you'll have a Z down there. Now, the Z that is down there is called the atomic number. The atomic number. And the A is called the mass number. Mass number, all right? And what it's about is each of the atomic numbers, okay, is going to be the number of protons. Number of protons, okay? Now, the number of protons must be balanced out by number of electrons over there, okay? Now, in this scenario, what we've got is we've got protons and we've got the electrons. And always remember, it's an element, therefore no charge. Protons equals electrons. So let's have a look, for example. In helium, we've got 2 protons, 2 electrons. Okay, that's what keeps it in balance. The next side of it, okay, is we've got to have a look and see, all right, let's just see what happens now if we go up to element number 3, lithium, right? Now, lithium is element number 3, right? And it's got 3 protons and 3 electrons in it. We need to devise how are these 3 electrons going to be put into this, all right? We'll go back to the atomic number and some of those calcs in a little while, all right? Right, so what we've got to do is we say, okay, the 3 protons, they sit inside the nucleus over there, okay? On the outside, we've got to come up with a packing pattern for the electrons, right? Because they're spinning around the nucleus. It kind of, if you look at it, inside the tennis ball will be the protons, and here on the surface is where the electrons spin around. Now, you may or may not have heard of something called Heisenberg's uncertainty principle. Basically, it means you actually don't know where the electron is. It's kind of occupying a surface. It's a fuzzy little chap. It's got a mass, it's got a velocity or whatever, but it's occupying a surface. Generally, the electron sits this side, the other one that side, and you can see they can spin around the outside of the tennis ball like that. Okay? That's how they actually work. They sit on the outside of the surface. But now if we add another one, we have to put them in a different position. Okay? But before we get to the electron configuration, let's look at a word, okay, that you may or may not have heard of. It's an isotope. Okay? What's an isotope? Well, first of all, we've got hydrogen, right? Let's just look. We've got hydrogen here. Hydrogen's over there. Remember we said this is 1H1. You also get this, 2H1, and you get 3H1 as well. Now, let's have a look here. This one here is called deuterium, like that, and this one's called tritium. Let me get my spelling right. Right? Now we said here at the bottom, let me just highlight this one over here, all right? This one here was the number of protons and electrons. So here we've got 1 proton, 1 electron. Okay, that's now all tied up. But what about here? Here we've got 1 proton, 1 electron, 1 proton, 1 electron, right? So there's no charge, but there's a 2 and a 3. What is going on over there? Actually, this is what is happening with an isotope. What it means is it means on the top, over here, the total number of particles in the atom is 1 proton, 1 electron. But here, whoa, here there's an extra 1 sitting in there. There's 1 neutron inside here. Here we've got 2 neutrons that are sitting inside there. Okay? Because we've got 3 minus 1, so there's 2 neutrons, right? So the number of neutrons, okay, is going to be equal to the 3 minus the 1. The 3 minus the 1. Okay? So it's going to be the number of minus the number of protons. Okay? So in any situation, and in your textbooks you're going to see where you balance these across, you can work out how many neutrons are inside there. What does it mean? It means that there's 2 particles inside there that have got no, let me just take these guys here. Okay, let's take here, we've got our proton and we've got our electron sitting over there like that. These 2 are now added into the mix. These 2 sit here as 2 independent, non-charged, they're neutral particles that actually sit into the atom, but they are put into the core, right? So the electrons are floating around over here, and these 2 neutrons are sitting inside the middle over there. Essentially, these here are responsible for radioactive decay. Okay? They split apart and they give us various other elements that come into play. That's how radioactive decay works. So what we've got now is we've got an isotope. All it is, it's the same element of hydrogen, it's just got extra neutrons built into it. There's isotopes of many things, okay? Chlorine has got isotopes. Cl35, Cl37. They are isotopes. Okay? Let's look at when they talk about relative atomic mass, okay? Now, relative atomic mass, as we said, let's just go back to this one over here, all right? Each, in here, let's say we've got hydrogen, so we've got 1 proton is positive, plus 1 electron inside here. Now, if you look on the standard handouts that you're going to be getting as you move through, you'll see the mass of an electron and proton are given to you. Okay? It's very, very small, but they are given to you. So you don't have to remember them, but what have we got? Inside we've got an electron and a proton. Okay? So that gives us the mass. But now, that's for hydrogen. But now we've got deuterium where we've got an extra neutron sitting inside there. So we've got to add its weight, right? For tritium, we've got to add its weight as well. So we've got to add the masses of all the particles inside to work out what the atomic mass actually is of one atom, one atom of hydrogen or helium or whatever, okay? Now, if you look on your periodic table at chlorine, you will see that they give you element number, all right? And they'll give you element number for chlorine 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? It's element number 17, right? And you'll see at 35.5, okay? This is called the relative atomic mass, okay? Well, what does it mean? All the numbers underneath there actually mean That is the mass of that particular element, okay? When we get to something called stoichiometry, where we measure the masses and things, and we actually use the relationships between, what we'll do then is we'll actually define it just a bit more closely regarding something called a mole. But at the moment, that's called the relative atomic mass, okay? It's relative. If you look, hydrogen is 1. Originally, hydrogen was given the unit 1. Essentially, we've moved to carbon now, which is number 12, right? It's given an atomic mass of 12, right? What essentially we've got is, don't forget that out there we've got, right? We have got hydrogen. We've also got deuterium, and we've also got tritium. We've got chlorine 35 and chlorine 37, right? How did we get to 35.5, right? Let's just go back to our atomic construction, okay? Essentially, here's our hydrogen, remember? Our proton and our electron, okay? Now what happens is we add in, okay? This is the hydrogen, so now there's this stuff floating around. That's over there. But we've also got a little bit of this, haven't we? So we've got to, in all of hydrogen, we've got to add this lot that's only the 2, plus we've got some of these. So we've got to add that in. And we've got some of these, right? So if you take a sample of hydrogen gas, you're going to get mostly this, but you're going to get 1 or 2 of these in there and 1 or 2 of those in there as well, right? So statistically, that's the majority, the bulk of it, but there's some of these, right? And some of these. These are the isotopes, aren't they? Right? That come into play. Now, in any sample, let us say we take chlorine, for example, all right? Okay? And we say, right, in any 100 grams that we take, all right? In any 100 grams, we have got 75.5% of the Cl35, right? But we've also got 24.5% of the Cl37, right? So what we've got is we've got a whole chunk of, I'm just going to take this one now. A whole chunk of, this is Cl35, which is the majority, right? Okay. Which means that in that case, we've got Cl35, okay? And it's number 17. So there's 17 protons, 17 electrons, right? 17 electrons, because protons must equal. It's number 17, remember? Each one goes up by a proton or an electron, whichever way you want to think about it. So you've got 34, so you've got 1 neutron here, okay? This is in chlorine 35. Let's have a look at the other one. We've got 17 protons, 17 electrons, that's 34, and we've got 37, which means we've got 3 neutrons in Cl37, right? That's the majority. But in any sample you take, you've got these, 75.5% is that. Okay, 24.5% is these. So overall, right, in the sample, it means, if you think about it, 100 grams or whichever way you want to look at it, we've got 75.5 of that, 25.5 of that, right? So how do we work out the relative atomic mass? Okay, well, basically what we do, we say here, we've got 0.755 times 35 plus 0.245 times 37. That's if you think, that adds up to 1, doesn't it? So for every 1 gram or 100 grams, you're going to have a ratio. So what do we get? we end up with 0.755 times that, 0.245 times that. That gives us, well, let's just work it out over here. 0.755 times 35 is equal to 26.42 plus 0.245 times 37 is equal to 9.06, okay, and plus 26.42 equals 35.48, 35.5. So the relative atomic mass is the mass of, if you took a sample of chlorine, a sample of hydrogen, it includes all the isotopes that come with it. So no, if our substance has no isotopes at all, then the relative atomic mass is the mass of its electrons, its protons, and its neutrons. Okay? That's the relative atomic mass, is the actual atomic mass. But if we have isotopes, we have to bring those isotopes into consideration. We can't ignore them. That is the process of how we go about doing that. Now, on the next side of it, we've got to say to ourselves, right, in these isotopes over here, okay, we've got that. We see on the periodic table, if you look at everything on the periodic table, all right, let me just grab a book over here. Okay, if you look at the periodic table, you will see, for example, hydrogen is actually 1.0079. So we've got 1.0079 is the relative atomic mass of hydrogen, right? This here, one, remember, was just hydrogen on its own with one proton and one electron, like that, right? But this bit here accounts for the fact that we've got, in some cases, that plus, I don't know why I keep writing a thingy down there, plus a neutron, and a plus minus and two neutrons. That number accounts for that. Look, for example, at carbon. It's 12.011. Why? Because we've got carbon 12 and carbon 14. Carbon 14 has got neutrons in it. Okay? How many? Well, let's have a look at it. Okay? We've got this carbon 12, right? Has got 12 protons, 12 electrons. That makes it neutral. Carbon 14 has got 12 protons, 12 electrons. All right. Kevin. Okay. Right. All of those are evened out. Right. But we've got 14. Right. Which means you've got 2 neutrons sitting in there as well. Okay. To get to the 14. Okay. Now that's what you may have heard of carbon dating. When they do archaeological discoveries, they find all the prehistoric bones or trees or whatever. Inside is carbon. But because of the percentage of carbon 14 is an isotope, isn't it? Okay? This is an isotope. What happens is it undergoes what's called radioactive decay. So over a period of time, these carbon 14 atoms start decaying back to carbon 12. The neutrons, let's say, disappear in a burst of energy. This process here allows us to date fairly accurately how old that relic is that's been found. Okay? So on all of the periodic table, those atomic masses at the bottom are actually accounting for, look, for example, at, let's have a look. Well, chlorine is there. There's a few of them. Let's look at copper. Look at copper. Copper is, in fact, 63.546. 63.546. Okay? which means that we've got different isotopes that we have to account for in copper. That essentially is what that is all about, right? Now, the next part that we're going to do is we're going to look at how do we pack the electrons in. This is a very important section because it deals with how we pack, how they're going to orbit the middle, and what do we do with this. We're going to look at things like the Lewis diagrams, the dot and the cross diagrams. We're going to look at how substances actually get together with the interaction of the orbitals. We're going to look at the energies involved in that, things like ionization energy. We're going to look at electron affinity. We're going to look at a few odds and ends that allow us to predict how atoms actually get together to form molecules, how molecules get together to form compounds. We're heading now into the building blocks of how we use the periodic table and everything and all the numbers that are in it, how we're going to use it to predict what it looks like, how much of it actually acts with something else. This is where we're going to start getting into the real nitty-gritty of it. And yeah, we'll be back and hopefully we can get ahead with this one. We'll do some examples, as I say, right at the end. In the next piece, I'll do some examples of actually the chemicals themselves with the different orbitals.